So today what I want to do is talk about three types of motion that you encounter with rigid bodies. And those three types of motion are going to be defined first. I'm just going to show you examples of what it looks like and how they sort of behave, and then start looking at what the tools are necessary to do the analysis. And you got to realize that this is the start of one of the more complex parts of the course, because up until now we've dealt with particle kinematics, particle kinetics, and you don't worry about geometry. Now you worry about geometry. And so you have an object that has both mass and now mass and size. We don't deal with forces in this chapter because it's kinematics. We start to only look at the effect of size. So there are three types of motion that you can expect. The first one is translation. So here, for example, the object translates in a straight line motion. You'll notice that the orientation of A to B doesn't change, nor does the relative position. So those remain constant throughout this whole operation. Now, if it travels along a curved path, same thing happens. But this distance and this angle remains the same. And so when we talk about translation, we're talking about an object that doesn't have any motion in the end. So if you have rotation, though, you have an object that's rotating about a fixed point. So say, for example, right there, and everything is occurring about there. There's no motion, no translational motion of the body. It only rotates about a fixed point. And you'll find that in later parts of the course, we start to look, especially in the next chapter, in this chapter, next chapter, everywhere up until vibrations, we look a lot at vibration or rotation problems. So just to define things, a distance from an object from the origin to point A is R. And I'm going to have now three different variables that appear. Angular position, which deals, say, with a theta. Omega, which is angular velocity. And alpha, which is angular acceleration. And you can immediately see that that sort of corresponds to x, v, and a, dependent on what you're looking at here. For general plane motion, which is the last type of motion we look at in the course, it is a combination of both rotation and translation. So you see that there the object has gone through some sort of crazy motion before moving off to the end point. Now, it ends up with the same orientation. It doesn't necessarily have to. It's just that I was lazy with my animations. So again, combines translation and rotation, and we have to start defining things a little bit more carefully. So we have distance from A relative to B. So A relative to B means that B is going to be in the numerator, and that tells me where everything is a reference to. A is the point of interest. And in order to make this work, I'm going to define a velocity of B and say that the entire object translates with a velocity of B. And then in order to return it to its final correct position, I have to put a rotation, and that's velocity of A relative to B. So velocity of A is equal to velocity of B plus velocity of A relative to B. And this equation is going to start taking the form of this. And I know I'm correct if I know that velocity of A equals velocity of B, or velocity of A, because these two terms will cancel. It's just the notation. And that's sort of what a vector diagram would look like for these things. So let's start looking at the various cases. So translation is the first one. And here I'm going to define two coordinate systems, x and y, x prime and y prime. I'm going to define, with respect to an origin at O, a distance r sub A, which is a vector, and a distance r sub B, which is also another vector. So this goes from here to here. But I can also define position B with respect to position A, and I'll have there, in that translating coordinate, a new vector, which is going to be RB with respect to A. And so position of B from here to here can be defined by the vector sum of RA plus RB relative to A. And you'll remember this from the kinematics chapter where you had similar problems to deal with, and you've talked about this in the past. So if we go to velocity, well, I can write RB equals RA plus RB relative to A, so that's good. That's my original position expression, and I can differentiate it. And differentiating it means that I'm taking the position and the rate of change of position with respect to time, and I have drB dt, dra dt, and drB with respect to A dt. Now, both of these terms, first two terms, go to velocity v, velocity A. But I know that A and B, which I may have messed them up in terms of, never change in terms of the total distance, nor do they change in the angle. And so this last term goes to 0. And velocity of B is equal to velocity of A for the general case, or for the particular case, of rigid body translation. And if I do that with acceleration, I can do the same thing, take the differential, and I get the not surprising result that acceleration of B equals acceleration of A. And so what I can sort of say there is all points in a rigid body subjected to either rectilinear or curvilinear translation move with the same velocity and acceleration. And you kind of end up with these expressions right here. So this is just a slightly more complex form of this. And what I've done is I've said, well, I have unit vectors which sort of correspond to these directions, which are my x, y, and z. I have r equals rxi plus ryj plus rzk. R is also equal to, in normal Cartesian coordinates, xi, yj, zk, and I can do that with velocity, vx in the I direction, vy in the j direction, vz in the k direction. And so I'm going to use my unit vectors to give me directions, and I'll leave these as sort of magnitude terms. Same thing with acceleration, acceleration x, y, and z in the I, j, and k direction. Now this is only for the particular case where the body has no translation. So that's great. That's case 1. Now let's go to case 2. Case 2 is rotation about a fixed axis, and this is, we're going to talk about velocity. So I've got a really complex diagram here. I'm just going to talk a little bit about it. I have a rigid body, and that's rotating about that fixed axis, so AA prime. I have a point B on the body and a point P somewhere on the edge of the body. Now I can define that point P in a number of different ways, but I can define it from some arbitrary origin, or I can define it from a planar origin. And often in this course I'm going to switch immediately to the planar origin, but it's kind of useful to look at it from this perspective. And if you do that, you also can sort of draw some normals, and you can sort of see very poorly in my diagram that this is rotating in this direction. I also have now put down my unit vectors in here with the rotation. So if I have a velocity vector somewhere out here, that's equal to the rate of change of r, which should be right there. And it is dr dt of the particle is tangent to the path with the magnitude v ds dt. And s, remember, is a path variable, and it's just a magnitude. And s goes as bp delta theta. Okay, so what does that mean? Sort of overhead view, I have bp. This is the same thing, I'm just looking down on it. And at some time, it's going to rotate a distance delta theta to a new p prime position. And I can sort of redefine that as r sine of psi, or phi, excuse me, this phi down here, delta theta, or v is equal to the limit as delta t approaches 0, r sine phi, delta theta, delta t, or r, not very easy to see, theta dot. Now, just for definition's sake, when I put a dot on something, whatever it is, it's going to be a first derivative. 2 dots corresponds to a second derivative. Same result could be done with cross products. V equals omega cross r. and omega is equal to theta k. So this right here, theta dot k. So that's where this is coming from, and that's where omega is. So this looks a lot more complex. It's actually not that bad, and you need to do a couple examples to be comfortable with it. But really, I mean, ultimately, the point here is that angular position at the instant shown in the figure, the angular position of R is defined by the angle theta. Theta is that angle that is within the plane, and that does that rotation there. Measured between a fixed reference line, and that's my fixed reference line over here, and R. So it's right to there. Displacement is just the delta theta, and that's my delta theta over here from an overhead view. So I have angular position, I have angular displacement, and I'm kind of going into these velocities. And I want to define a couple things. So I have omega, which is just going to be d theta dt, and it's just sort of rotating through here. And d theta, say for example, if I go through a small displacement from P to P prime, over some time, delta t or dt, I'm going to get that sort of result. Now, I've kind of done engineering math here where I've taken delta theta, delta t, and drawn it there, and said d theta, dt, but the idea is basically for very infinitesimal displacements, I can write omega as that. And omega and alpha, which is my other term, is going to be sort of my, again, angular velocity and acceleration. And you've got to get used to this notation because you're going to use it a lot. Counterclockwise, because the world is right-handed, is positive. And so counterclockwise just means this. And it's possible, if you take a look at one of the first videos I did in this series, I have a picture of my thumb pointing upwards and rotating around. The other thing that you have is angular acceleration. Alpha is equal to the derivative d omega dt, which again is not a surprise, and it should be something that you kind of recognize from a equals dv dt. And alpha is equal to d omega dt, but it's also equal to d squared, or the second derivative of theta with respect to position. So again, angular acceleration does not necessarily go in the same direction as velocity, and the direction is highly dependent on what's happening at that instant. And let's talk a little bit more about it. If you have rotation about a fixed axis, you can also sort of write alpha equals to omega d theta, which kind of, again, should remind you of this expression right here, which you've already derived, and we do our usual sort of game of splitting terms up, and we end up with this relationship alpha d theta omega d omega. For constant angular accelerations, you get similar results as you got in the past. So omega is equal to omega naught plus alpha ct. Theta equals theta naught plus omega naught t plus 1/2 alpha ct squared. And omega squared equals omega naught squared plus twice alpha c theta minus theta naught. So I'm just giving you a lot of definition here in this particular lecture, not necessarily tied too much to the rotation, but because I'm introducing these new variables, I'm throwing this in right here because I think it's useful to talk about it. So velocity can be sort of separated into, not very well done, into its polar coordinates, VR, and I just covered it up, equals r dot, v theta equals r theta dot. And if r is constant, that means dr dt equals 0. And v theta equals r theta dot, but it doesn't equal 0, pardon me. I'm just going to scratch that out very badly. But I get that theta dot is equal to v equals r omega. And I don't know, I think I just copied a formula and I forgot to fix it when I did the copy. So now I have a relationship for velocity, but the big velocity relationship I have, v theta, which equals v. So my velocity in a fixed axis condition is really only my v theta component of velocity. So if I have rotation about a fixed point, and again I've got a very complex diagram where I have an origin down here, I have rp, which defines the distance to this, r, which is the distance to here, and I have v, which is acting in this way. V is equal to omega cross rp, but it's really just equal to this component. This component does nothing because it's acting in the same line as the angular velocity, theta k. So it's parallel. So if I write it that way, I'm going to end up with really this relationship here, which is v equals omega cross r. Now, the other thing that you need to know is, and I don't need to write this really as anymore as an vector, but an is equal to the acceleration of the body, or acceleration of point P with respect to the center, and it's defined along that radial line, and it's defined in the direction normal. And so it points in towards the center of curvature, and it's going to be omega squared r. It also, you've seen it before, as v squared over r. Alpha acceleration tangential is just going to be alpha with respect to r. If the speed of p is increasing, the point P, acceleration is in the same direction. Acceleration tangential is in the same direction. If p is decreasing in speed, acceleration tangential is in the opposite direction. And if p is constant velocity, then it is also occurring. Acceleration tangential is equal to 0. Now, if acceleration tangential is equal to 0, that does not mean that the acceleration normal is equal to 0, because it's dependent on velocity. So you can have a normal acceleration despite the fact that you have constant velocity, because you have to remember the definition of acceleration is not rate of change of speed, it's rate of change of speed and direction. So I've kind of jumped ahead to the big reveal. Normal component of acceleration, time rate of change in the velocity's direction. It's always pointing in towards the center of curvature, O, and the acceleration of point P now can be described as a combination. So you're going to have d omega, say d omega dt, which is alpha angular acceleration, and it can be written as alpha omega dot or theta double dot. But really, it's kind of important to recognize that I can also write this as a vector. And this vector term is right here, dv dt, d omega dt cross with rp. I'm going to make it r later. Omega cross with drp dt, or alpha cross rp, omega cross rp. And if I have it within the plane, so if it's like this, and I have r, o, and I have omega and I have alpha, I can write that as alpha cross r plus omega cross r. And that's my tangential acceleration, at, and that's my normal acceleration, an. And so the expression I'm looking for here in the end is that the acceleration of tangential, the acceleration is equal to the acceleration tangential plus the acceleration normal. Now, if I solve through this term and I'm doing this plane as a plane, I always get omega minus omega squared r, and I get alpha cross r. So that's my governing equation. It should be written again because I use different notation every time I write these things, as this right here. since AT and AN are perpendicular, the magnitude of acceleration is just the squared sum square rooted, and that gives you the acceleration magnitude. So general plane motion is going to combine velocity A with respect to B is R A with respect to B omega, or as a vector term, omega cross RA with respect to B. You got velocity, and so you've got to realize that you're going to deal with that component as you go through this. And what else? Velocity is equal to translation plus rotation. So it's always going to be a translational component, that one, and a rotational component. The analysis is not that bad. You just, it's overwhelming the first time you see it. It's overwhelming the 10th time you see it. But if you do enough of this, you'll really get comfortable with it, and you'll really get really skilled at it. Now, the other thing you should be aware of, I often find that a vector approach like this, just for the velocity right now, is enough to sort of start out with this. And that's where I kind of, I'm leaving this right now. So again, you have a vector sum, you get a vector result, and so if I want velocity of A, it's velocity of B plus velocity of A relative to B, and if I had wanted velocity of A, my velocity of B with respect to A would be the same arrow, or same line, with an opposite arrow. So, general plane motion, again, just the sum of translation and rotation. And ultimately, the goal here, and I hope it's come across, is that these three types of motions have been identified. We kind of discussed what the differences are, and particularly how they're related. And so you're going to spend a lot of time with this. The next step in terms of the discussion is to take these ideas and use them as the basis for the next step, which is analyzing results. And so you'll see some example videos also, but this is the definition, and you really got to start here. All right, and we'll talk again later.